Okay, so am I audible?
Yes, sir, you're audible, sir.
Okay, fine.
Yes, sir.
Okay, so my first thing aim is basically I want to recall few things from week 1. So then after that I will start taking your questions. Okay, so let me first recall few things. Briefly I'll recall. Okay, so before that let me share my screen. Okay, so my screen is visible, right?
Yes,
Okay, okay, fine.
Yes,
Okay.
sir.
Yes, thanks. Okay, so so let me start with matrix. So what is, okay, so the first thing is matrix. So matrix is basically it's a bunch of numbers in a rectangular box, and they are basically arranged in rows and columns. Okay, so for example, if I so a matrix is something like this. So it's a rectangular box and few things are arranged in some columns and as well as in rows. Okay, so so from here what I can say, so how many rows this particular matrix has. So as you can see, this is a row, right? This is a row of this matrix, and as well as this is also a row of this matrix. Okay, so this matrix has 2 rows, right? Okay, so first thing is all these things maybe these are obvious for you, but let me recall. So this matrix, as you can see, this matrix has 2 rows. Okay, and what about the number of columns? Right, so similarly you can see this matrix has 3 columns. Like this is the first column of this matrix, right? This is the second column of this matrix, and this is the third column of this matrix. Okay, so since this matrix has 2 rows and 3 columns, so using column and row, we assign a order to this matrix. Okay, so basically this is a matrix of order 2 cross 3, right? 2 cross 3. This matrix, whatever this matrix is, let's say this matrix is A. This matrix is of order 2 cross 3. So this 2, the first thing, so in this notation, the first one represent the number of rows. Okay, and the second one represent the number of columns. Okay, so once you have a matrix, then that particular matrix has some order. Okay, so just by looking at the matrix, then we can easily tell that what is the order of this matrix. For example, if I take this matrix, let's say this is my matrix, new matrix, 1 2 3 4 5 6. What is the order of this matrix? 3 into 2. Okay, so because because as you can see, you have 3 rows. So this is my first row. Okay, so this is my second row, and this one is my third row. And similarly, I have 2 columns. Okay, so this one, this is my first column, and this is my second column. Okay, so this matrix is of order 3 cross 2 because it has 3 rows and 2 columns. So once I have a matrix, the next question is how I can tell about the entries of this matrix. Okay, so there is some notation for all the entries of the matrix. Okay, once so for example, let me take this matrix. So now what I want to do, once I have a matrix and I know I can assign an order to this matrix. Now I just assign some name to all the entries of the matrix. Okay, for example, let's say this matrix 1, 2, and 2, 4. So as you can see, this matrix, this number one is basically in the first row, right? So this number one is basically in the first row and in the first column. That's why this is basically the 1, 1th entry of the matrix, right? And similarly, this number 2, right? This is in your first row and second column. So that order is important. This is in first row and second column. That's why this is basically your 1, 2 entry of the matrix. Okay. And similarly, this 2, this is in second row and first column. That's why this is 2, 1 entry of the matrix. And similarly, this 4 is basically in second column and second row. This is 2, 2th entry of the matrix. So similarly, I can assign a name to all the entries of a matrix. So I don't have to specifically. So if I tell I'm talking about 1, 2th entry of the matrix, that means I'm mentioning these two. Okay, these two, not this one. Okay, so when I'm saying that 1, 2th entry of the matrix, then specifically I'm saying this two. Okay, not the below. Okay, so in this way we can assign a symbol, or maybe in some sense a name, to all the entries of a matrix. So let me quickly take some other example. Let's say this one, 0, 1, 7, 2, 9, 11. Okay. So first tell me, what is the order of this matrix?
2 by 3.
2 cross 3, sir.
Correct. Yes. So this is a matrix of order 2, 3. So what is this entry? 0,
1 1
A1
1, because it lies in the second, the first column as well as in the first row. First row as well as in the first column. What about this one? 1,
A1 2.
1, 2, because it basically lies in the first row and second column. And what about this one?
1 3.
1, 3, correct. And in the same way, this is 2, 1, right?
Yes.
And this is 2, 2, and this is 3, 2, 3. So in this way, we can assign a symbol to all the entries of the matrix. Okay. So this is basically all about the matrix. So the next thing is, there are some special type of matrix. Okay. So matrix, as you can see, so here the number of columns. So for example, if you see this matrix here, the number of columns and number of rows, they are different. Okay. So in some cases, in some matrix, the number of rows and number of columns, they coincide. That means the number of rows and number of columns, they are basically the same. So there is a special name for this type of matrix. So this type of matrix, we call this type of matrix as square matrix. Okay. So square matrix is a matrix where the number of rows and the number of columns, they are basically same. Okay. So for example, suppose consider this matrix. What is the order of this matrix?
Singleton 1.
1.
Correct. 1, right? This is a matrix of order 1 cross 1. Okay, so here the number of rows and number of columns, they are basically same. So this is an example of a square matrix. Right? This is an example of a square matrix. And similarly, if I consider this matrix 1, 2, 2, 3.
2 cross 2.
This is a square matrix because it has 2 rows and as well as 2 columns. Okay, and similarly I can construct a square matrix of order 3, right?
3 cross 3, 4 cross 4.
Yes, so for any natural number, I can construct a square matrix of that particular number. Okay, so let me take 1, 2, 3 or 5, 6, 7, maybe 8, 9, 10. Okay, this matrix has 3 rows and 3 columns. So this is a matrix of order 3 cross. So there is nothing special about 1, 2, 3. So if you give me any natural number, I can construct a matrix of square matrix of that order. Okay. So again, so square matrix contains so in particular square matrix contains lot of matrix. Okay, so many matrix come under square matrix. So again, there is a subcategory of square matrix. Okay, so that matrix is basically what? Diagonal matrix. Okay. So diagonal matrix is basically, it's a subcategory of square matrix. Okay. So basically, what is a diagonal matrix? Diagonal matrix is yes.
Sir, I have joined it. Sir, we have started with the concept or what? Sir?
I'm just basically revising the concept of week 1.
Okay, sir.
Yeah. So diagonal matrix matrices, whatever diagonal matrices I'll define. So this matrix, they basically comes under the class of square matrices. Okay, so diagonal matrix is basically, it's a square matrix where all the non-diagonal entries, okay, they are 0. Okay.
0.
So for example, if I consider this matrix, so a diagonal entry is basically all the entries that are in the diagonal. Okay, so for example, here, if you see, this is in the diagonal. Okay, 1 is in the diagonal. So here 3 is in the diagonal. Okay, so because diagonal means your I, ith entry. Okay. So here 1 is basically 1, 1 entry. This is a diagonal entry. And similarly, 3 is also a diagonal entry. This is 2, 2 entry. Okay. And for this particular 3 cross 3 matrix, here the diagonal elements are basically 1, 6, and 10. Okay. And diagonal, so the definition of diagonal matrix is that a square matrix is a diagonal matrix if all the non-diagonal entries are 0. Okay. So the first question is whether this is a diagonal. So according to the definition, whether this is a diagonal matrix.
No.
No.
Because,
No, sir.
Because
No.
correct. So because it says that all the non-diagonal entries are 0. Okay, so first thing I have to go and check whether all the non-diagonal entries are 0 or not. So if I go to, so this is a diagonal entry and this is a diagonal entry. So I don't care about diagonal entries. I just have to check for the non-diagonal entry. So this entry. So this entry, it's a non-diagonal entry, but it's non-zero. Okay. So this entry is non-diagonal entry and still it is non-zero. That means this cannot be a diagonal matrix. And so the next question is my next question is, what about this one? 0, 0, 0, 0. Whether this is a diagonal entry or not? Diagonal matrix.
Yes, sir.
No.
No, sir. No.
It's a null matrix, but we can also say that it's a diagonal
See, it's
matrix.
diagonal matrix also, no, sir, because diagonals are same and the other than non-diagonals are zeros.
No, it's no. I don't care whether diagonals are same or not. Okay, for a diagonal matrix, I really don't care whether the diagonals are same or not. What is the definition of
okay.
diagonal matrix? So diagonal matrix is basically a square matrix where all the non-diagonal entries are zero. Okay, so
Okay, okay,
so
sir.
It will be diagonal, sir. Diagonal.
so for the thing is here, what are the diagonal entries? 0 and 0. I don't care. Okay, I don't care about the diagonal entries. The only thing I care about the non-diagonal entries. If all the non-diagonal entries are 0, then only I can say that this is a diagonal matrix. So next thing, what I have to do, I have to check for all the non-diagonal entries. Okay, so this is a non-diagonal entry and this is a non-diagonal entry, and both of them are 0. Right, both the non-diagonal entries in this matrix are 0. That means this is a diagonal matrix. See, I don't care what are the diagonal entries. Only thing I care about the non-diagonal entries.
Okay, sir. Okay. It means we have to lie on the definition.
Correct.
Yeah.
So
Okay, sir.
so for example, yes.
Question. Sir, is
So-
1 by 1 matrix is a diagonal matrix?
Sorry.
It is 1 by 1 matrix, means it contains only one singleton element.
Yeah, it's always diagonal matrix because this matrix don't have any non-diagonal entries. Since this matrix don't have any non-diagonal entries, then I don't have to check anything, right? Because the definition says a square matrix is a diagonal matrix if all the non-diagonal entries are 0. Okay. Since this matrix don't have any non-diagonal entries, so then this condition is vacuously true. Right? It says that if a matrix has some non-diagonal entries, then all the non-diagonal entries are 0. Okay. But here, this matrix doesn't have any non-diagonal entries, so I don't have to check. So this is vacuously a diagonal matrix. Clear?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So what about this one?
So the second one, diagonal matrix,
Hmm.
but the remaining two are also diagonal elements, na sir?
Which one? You are talking about this one?
Yeah. The zeros with two lines underneath, they are also diagonal, na?
No. So what is again, like, can you tell?
In
So
matrix concept, sir, it is ith entry that is called the diagonal entry, right?
yes. These are the diagonal entries. Okay.
I should be equals to j.
So when I comma so basically I comma I are the only diagonal entries. This is what is the name of this entry? Like this is 1, 2, right?
Yes, sir.
So here I and j are different, right? So
Okay.
this cannot be a diagonal entry. Okay. So what about this one? This is 2, 1. So here I and j, they are different. That means this cannot be a diagonal entry. But here this is 1, 1. So here I and j, they are same. Similarly for here also I and j, they are same.
Same.
Okay.
Yes, sir.
Now got it.
Yes. So only thing for it, yeah. So for let me again
Complete. Yes,
tell
sir.
you the same thing. So basically, what you need to check for a diagonal matrix, what you need to check? You need to check all the non-diagonal entries. Okay. If all the non-diagonal entries are 0, then only you can say that particular matrix is a diagonal matrix. Yes. Any questions?
Sir, this diagonal is called leading diagonal, right?
Okay, so you can say that leading diagonal, but okay, so we're not going to use that probably in our course.
Sir, excuse me.
Yes.
Is it not that all diagonal elements are different from 0? It's not like that, sir.
No. Diagonal elements can be 0.
Can be 0. Okay. Thank you, sir.
Diagonal entry, they can take anything. Okay, so
Yeah,
diagonal
yeah.
entry, they can take anything, but the non-diagonal entries
Should be zeros.
should be 0. Yeah.
Yes, sir. Got it, sir.
Sir, can you explain one more time, sir? Just third example. How single element is a diagonal.
No, here this one you are talking about
Yeah,
this
yeah,
one.
yes.
So because here there is only one entry, right?
Yes,
In this matrix there is only one entry,
yes.
and that entry is a diagonal entry, right? This is a diagonal entry. This is basically 1, 1, right?
Actually, 1, 1.
So this matrix don't have any non-diagonal entries. So then I don't have to check, right? Because I have, so for a diagonal matrix, I have to check for non-diagonal entries. Okay, since this matrix don't have any non-diagonal entries, so I don't have to check. Okay, so this is vacuously, this is a diagonal matrix.
Can you write the term which you are saying vacuously?
Vacuously means, okay, so this is basically obviously, like, so in some sense, so what basically I can probably you'll see a few examples like when basically vacuously something is correct. Okay. Okay, so okay, let me take one more example. Let's say
So in other words, we can say that it is not meeting the condition, but at the same time, it is not contradicting the condition as well.
no, it's not meeting the condition. If certainly it's not meeting the condition, then certainly you cannot say it as a diagonal matrix. Okay, see so the thing is, in condition something is given. Okay, so in the condition, in the diagonal matrix definition, if basically if I write the diagonal matrix definition, what basically I can say, a square matrix is a diagonal matrix. Okay, so in a square matrix is a diagonal matrix when all the non-diagonal entries are 0. Okay, can you mute? Okay, so the definition says a square matrix is a diagonal matrix if all the non-diagonal entries are 0. Okay, so it's basically saying that when the matrix has a non-diagonal entry, then that entry has to be 0. That is basically the definition. In diagonal matrix definition is saying when the matrix has a non-diagonal entry, and then this entry has to be 0. Okay, since this matrix don't have any non-diagonal entries, then this is vacuously true. That is my point. Okay. So when I have to go and check one entry is 0 or not, that I have to do when the matrix has a non-diagonal entry. Okay, since this matrix don't have any non-diagonal entry, so I don't have to go and check that. Okay. So there is nothing to check here. So that's why I'm saying this is vacuously correct. Okay, so let me take this example. 1, 3, 5, sorry, 0, 0, 0, 0, 0, 0. What about this matrix?
Yes, sir.
Diagonal matrix.
So it is a diagonal matrix because again,
Yes, sir.
I first thing what I have to do, I have to omit all the non-diagonal diagonal entries. Okay, so I don't care about all the values that are in diagonal entries. Only thing I have to go and check the condition about all the non-diagonal entries. So this is a non-diagonal entry and this is 0. This is a non-diagonal entry and this is 0. This is a non-diagonal entry, this is 0. This is a non-diagonal entry, this is also 0. This is also 0, this is 0. So all the non-diagonal entries, they are 0. That means this is a diagonal matrix. Clear? So now you can differentiate between diagonal and non-diagonal.
Please repeat it once more.
Sorry?
Repeat it at last diagonal matrix.
Sorry? I can't hear you.
Please repeat it. Last one.
No. Can you repeat? It's not audible.
Yeah, can you repeat it? Last diagonal matrix. How it can be diagonal matrix?
No, I explained it, right?
No, this last one. 1 0 0 0 0 0 0 0 2.
So the thing is, what about all the non-diagonal entries of the matrix, whether they are 0 or not? What about for this matrix, let's say this A, what about all the non-diagonal entries of this matrix, whether they all of them are 0 or not?
Okay.
Since all of them are 0, that's why this is a diagonal matrix.
Okay.
Please mute yourself. Whenever you are not talking, please mute yourself. Okay. Okay. So again, one more subclass of diagonal matrix, that is called scalar matrix. Okay. So scalar matrix is basically, it's a subclass of diagonal matrix. So here actually you need one extra condition. So scalar matrix is basically a matrix, a diagonal matrix. Okay. This is a diagonal matrix plus one more condition. And what is that condition? All the diagonal entries
should be non-zero.
Should be same.
Okay.
Should be same. Okay. So as you can see, for the scalar matrix, you have two things. First thing, it has to be a diagonal matrix. Okay. So first thing, it has to be a diagonal matrix. And second thing, all the diagonal entry of that diagonal matrix should be same. Okay. So let me take this example. Okay, so this is a matrix. So my first question is whether this is a scalar matrix or not.
No.
No, sir.
No.
So for
No,
the
sir.
as you can see, for the scalar matrix, you need to check two conditions. Okay, this one and this one. So the first thing is whether this is a diagonal matrix.
Yes.
Yes, this is a diagonal matrix. So the first condition holds. Okay, and the second condition says all the diagonal entries should be same. So here, as you can see, all the diagonal entries, they are different, right? So in the first diagonal, you have 1. In the second diagonal, you have 2. In the third diagonal, you have 3. So all the diagonal entries, they are different. That means this is a diagonal matrix, but this is not a scalar matrix. Not a scalar matrix. Okay, so this is not a scalar matrix. Let me take one more example. 1, 1, 0, 1. So my next question is whether this is a scalar matrix or not.
No, sir.
No, sir.
No, sir.
No, sir.
So this
No,
is
because one is there. Diagonal.
So this is not a scalar matrix, because again, first thing what we have to check whether this matrix is a diagonal matrix or not. Okay, so as you can see, this is not a diagonal matrix, because here this one. So if you see this 1, 2th entry, which is a non-diagonal entry, and this non-diagonal entry is non-zero. Okay, so that means this is not a diagonal entry. Sorry, diagonal matrix. And since this is not a diagonal matrix, that means this cannot be a scalar matrix. This cannot be a scalar matrix. Okay. So okay, so the first so again let me recall. So you need to check two conditions for a scalar matrix. First this has to be a diagonal matrix, and second thing, all the diagonal entries should be equal for that matrix. Okay, let me take the last example. What about this matrix? Whether this is a scalar matrix or not?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
It is.
Yes, because certainly this is a diagonal matrix, and as you can see, all the entries in the diagonal, they are basically same, 0. Okay, so here you have 0, here you have 0. Okay, this is a diagonal matrix, and plus all the entries of that matrix are basically 0. Okay. So this is also a scalar matrix. So any doubt till now?
No doubt, sir.
No, sir.
No, sir.
All clear.
No, it's clear.
Okay, so one of the maybe I say one of the most important scalar matrix is basically identity matrix. Okay, so identity matrix is a scalar matrix where all the diagonal entries are 1. Okay, so this is a identity matrix, okay, of order 2 cross 2. Okay, this is a identity matrix. Okay, this is one of the most important matrix that basically you will later you will see. So again, so this is okay. See, if I write like this, then this is basically a identity matrix of order 3.
Am I audible?
This is an identity matrix of order 3. So so basically we denote this identity matrix as I. Okay, I 3 cross 3.
Sir, for 1 cross 1 matrix,
Hello?
identity matrix, 1 should be there only, right?
Yes, correct. This is the identity matrix of order 1 cross 1.
And sir, it will be a scalar
Identity
matrix
matrix,
as well as an
scalar matrix, all right.
Yeah, correct.
So all scalar matrix or identity matrix, sir?
No. So
Only
when
one
All
should be
identity
there.
or scalar?
no, so when in a scalar matrix, all the diagonal entries are
Same.
basically 1. Okay,
Hmm.
1. Then only you say that identity has an identity matrix. Okay. So for
Yes,
example,
sir. So that I'm asking that we can say all identity matrix or scalar matrix
yes.
because all the diagonal elements are
Yes,
same.
yes. Identity matrix is a scalar matrix. All the identity matrix, they are basically scalar matrix. But the converse is not true. Okay, a scalar matrix.
Yes, sir. But the reverse is
certainly,
not true. Okay.
yeah. For example, if I take this matrix 2, 0, 0, 2, this is a scalar matrix, right? This is a scalar
Yes, sir.
matrix, but this is not.
But not identity matrix.
Not identity matrix.
Okay, sir.
Yes.
Clear.
Okay, so once now. Now once you have matrix, the next thing is we can add matrix and we can multiply a scalar with a matrix. Okay, so and one more thing I just want to tell you that when two matrices have same order, then only you can add these two matrices. Okay, if two matrices are of different order, then certainly you cannot add these two matrices. Okay, so for example, if I want to, so this addition of these two matrices has no meaning. Because this is a matrix of order 2 cross 2 and this is a matrix of order
2 cross 1.
2 cross 1. So as you can see, both the matrices, they are of different order. So this addition of this kind of matrix has no meaning. Okay, I can add two matrices when they are of the same order. Okay, for example, if I take this matrix 1, 2 plus 2, 1, then I can talk about the addition of these two matrices because they are of the same order. The first matrix is 2, 1, second matrix is 2, 1. So, and how you add these two matrices component wise. Okay, so you add this. This is basically 1, 1th entry, and you add the 1, 1 entry of this matrix, the first matrix, with the 1, 1 entry of the second matrix, which is 2. So if you add, you will get 3. And similarly, you add the 2, 1th entry of the first matrix with the 2, 1th entry of the second matrix. So here you will get 3. So in this way, you can. So there is nothing special about this particular 2 cross 1 matrix. So you can add basically any m cross n matrix with with maybe some other m cross n matrix. Okay. So if the matrices are of the same order, you can always add them. So the next thing is you can multiply a scalar. So the next thing is you can multiply a scalar with a matrix. Okay, so C is a scalar, which is, let's say it's a real number. You can always multiply C with some matrix. A can be of any order. Okay, so what basically you have to do, you have to multiply C with all the entries of the matrix. Okay, so you just need to multiply C with all the entries of the matrix. So if C, you have a C, which is a real number. If you want to multiply with some 2 cross 2 matrix A, B, C, D, okay, then this is basically what you just need to multiply C with all the entries of the matrix. So the new matrix is C comma A, C comma B. Okay, okay. So let me take this C, not C, maybe something else, alpha. Okay, so if I multiply alpha with this matrix, I'll get alpha A
And alpha B,
alpha B, alpha C, and
alpha D.
So we just need to multiply all the number. So you just need to multiply the number with all the entries of the matrix. Okay, so that is how you multiply. That is how we define scalar multiplication with a matrix. Okay. So the next
Scalar is a constant here.
yes, it's a constant. So alpha can be any number, like alpha can be, let's say 0, alpha can be 1, or alpha can be pi. It can be any real number. Okay.
So we are calling this as scalar multiple matrix.
Yeah, so scalar multiplication of a matrix. We are basically multiplying a scalar with a matrix, right?
Okay.
So why we could not say that we are multiplying with a real number?
You can say that is not a problem. Okay, so the thing is, okay, so okay, so that you will see in the later. So basically real number are not the only numbers. Okay, so you have lot of numbers, okay, beyond real. Okay, so that's why we are using some general notion, like that's why we're using this as a scalar. Okay, so
Okay.
so when you are only dealing with real, then certainly you can say that alpha is a real. Okay, but this whatever we are discussing, these are not restricted to only reals. Okay, we can define for many general fields basically. Yeah.
Okay, thank you, sir.
Yeah. So okay, so the next thing, what so once we have matrix, we can add matrix and we can multiply a scalar with a matrix, and the next thing is basically we can multiply two matrices. Okay, so this is basically probably the most important thing, that we can multiply matrices. Okay. Okay, but okay, again under certain condition. Okay, when, so suppose I want to multiply a matrix A with another matrix B. So when this multiplication is well defined, that is really crucial. I cannot multiply any two arbitrary matrix of some arbitrary order. Okay, so that is not possible. For example, if I take this matrix 1, 2, what is the order of this matrix?
1 by 2.
1 cross 1.
1 cross 2.
1 cross 2.
2.
Sorry,
cross
sir.
2.
1 cross
Yeah.
2.
Okay, so certainly I cannot multiply this matrix with this matrix. So this multiplication has no meaning. Okay, so there is a condition on matrix multiplication. So when I can multiply two matrix, so suppose I have a matrix A, which is of order m cross n, and I have another matrix of B, which is of order R cross A. So the matrix multiplication is defined if and only if n is basically equals to R. Okay, so this basically what this says, that I can multiply the matrix A with B if the number of columns of A is same as the number of rows of B. When this condition holds, right? When this condition holds, then only you can multiply A with B. Okay, so for example, if you see this matrix, the above thing, so this is my A and this is my B. So here the number of columns of A is basically 2, right? And for B, the number of columns is 3. So they're different. So since they're different, I cannot multiply it. Okay. So okay, so now let's see when this particular condition holds, then how we can multiply two matrices. Okay, so let me take some example where this condition holds. So let's say this example 1, 2. This is basically 1 cross 2 matrix. So I have to take a matrix where the number of rows of that matrix is basically 2. Then only I can multiply with this A. So let's say 2, 2, 1, 2. Right? This is a 2 cross 2 matrix, right? So here the number of column of A, which is 2, is same as the number of rows of B, which is 2, right? So then I can multiply this matrix. Okay, and if I multiply, then what I will get? I will get a matrix of order 1 cross 2. Okay, 1 cross 2. Okay. So how basically I can do the multiplication? So basically what I have to do, I have to take the first row, then I have to multiply with the first column. Okay, so if I do component wise multiplication and then addition, what I will get here? What will be the first?
4.
Correct. So again, so this is, as I said, this is a 1 cross 2 matrix, right? So I should get one more entry, right?
6.
Which is
6.
so yes, correct. So I have to multiply this row with this column. Okay, then I'll get 6. Okay, so this is basically the product matrix.
The same condition is applicable for when we perform addition.
No, addition. So addition is something different, right? Addition, you can add two matrices if and only they are of the same order. Okay, so
A
you
square
can,
matrix.
even square, certainly you can. So even you can add two rectangular matrices. That is not the case. But for addition, you need. So for addition, they need to satisfy some different condition. What is that condition? If both the matrix, they are of the same order. So here you can see you can't add A and B, right? Because order of A is what? 1 cross 2, and order of B is what? 2 cross 2. Okay, so that means you cannot add these two matrices. Okay, but certainly you can multiply these two matrices. Okay, for addition, both the matrices, they have to be of the same order. Okay, is it clear?
Yes.
Okay.
Yes.
So similarly, okay, so similarly you can do it with the same more or less with the same procedure. You can multiply actually any two matrices that satisfy this condition. Obviously you have to check whether both the matrices, they satisfy this condition or not. And similarly, you can always multiply true matrices. Okay.
So once can you show how 4 and 6 came? I didn't get it.
No, what basically I'm doing. So this is my, so I'm multiplying the first row of this matrix, and this matrix certainly has only one row. Okay, I'm multiplying first row of this matrix with the first column of this.
So 1 into 2, 1 into 1.
So basically what I'm doing, 1 times 2, right?
Right.
Plus 2 times 1. So this is basically what? 4. Right. That's why I'm getting 4 here. Okay. And similarly, you can see that again, I'm doing the same thing. I'm multiplying the first row with the second column. Right. So what I'm doing, I'm multiplying 1 times 2, right?
Right.
Then I'm adding with 2 times 2, right?
Right. Okay.
Well, I'll get 6.
Right. Right. Okay. Thank you, sir.
Yeah. So, okay. So maybe let me take one more example. So 2, 3, 4, 5, maybe 0. So what is the order of this matrix? This is 2 cross 3, right?
Yes, sir.
So let me take a matrix with 3 rows. Okay, then only I can multiply. 1, 0, 0, 2, 1, 1. What is the order of this matrix?
3 by 2.
3 cross 2.
3 into 2.
3 cross 2. So this is my matrix A, and this is my matrix B. So can I multiply these two
Yes, sir.
matrices?
Yes, sir. Yes,
Yes,
sir.
sir.
Because the number of columns here is same as the number of rows. So if I multiply, what will be the order of the
2 cross 2.
2 into
Plus 2, sir.
2 cross 2.
So for the first entry, so 2 cross 2 means the matrix will be something like this, right? This is a square matrix. So for the first entry of this matrix, what I have to do? I have to multiply
The first row with the first column.
With first column.
Correct. So I have to multiply the first row with the first column. Okay. The first column. So if I multiply, what I will get? 1.
1.
Yeah,
One,
correct.
sir.
1 times 1 plus 2 times 0 plus 3 times 0, which is nothing but 1. And for this entry, which is basically 1, 2th entry, what I have to do?
7.
I have to multiply.
7,
Yes,
sir.
7.
7.
Basically, what we have to do? We have to multiply the first row
Second column.
with the
Second column.
So this is basically 1 times 2 plus 2
2 times
times
1,
1
3
plus
times 1,
3 times 1, which is 7.
7.
And similarly for here, with
Second row, first column.
this is basically second 2, 1th entry, which is second row. So for that, we have to multiply the second row with the first column. Okay. So similarly, you can
4.
multiply, you will get 4. And again, for this one, you have to multiply second row with the second column. So
13. 13.
you'll get
13.
yes. So this is my resultant matrix. Okay. So in this way, like there is nothing special about this 2 cross 3 or 2 cross 1. If you have any matrix of the from M cross N and N cross R, you can always multiply. Okay. So if so, what basically I'm trying to say, if I have a matrix of order M cross N and I have another matrix of order N cross R, I can always multiply these two matrices and I will get a matrix of order M cross
R.
Correct. Okay, so this is all about matrix multiplication. Okay, so the next two things probably I'll discuss. One is determinant of matrix, and one more thing is probably minor and cofactor. So okay, so again, so finding determinant is also more or less
Sir, also discuss, let's triangular
Linear
matrix.
equations also, sir.
Triangular matrix, sir.
yeah, I'll come to that. Okay, just remind. Okay, I may miss, so better if you remind me in the end. So before that, let me discuss these two things. Okay, so I'll quickly, because you already know how to compute the determinant, so there is no point of spending more time on that. Okay, again, determinant, you can't take determinant of any matrices. Okay, so for a so you can only take determinant of square matrices. The way determinant we have defined the determinant, you can only take the determinant of a square matrices. Okay, so determinant has meaning only for square matrices. So for example, the way we have defined the determinant of a 1 cross 1 matrix is basically, if this is a 1 cross 1 matrix, the determinant is basically A. Okay, so for example, if the determinant of this matrix is 1. Okay, so if I take a 2 cross 2 matrix A, B, C, D, then how we define the determinant?
AD minus BC.
Yes, correct. So you just have to multiply this opposite entry, and you have to subtract with the multiplication of these two opposite entries. So this is basically AD minus BC. So let me take example. For example, if I take 1, 3, 2, 2, the determinant of this matrix is nothing but multiply 1 with 2, you'll get 2 minus multiplication of, so this is 6, which is minus 4. Okay, so yeah, so this is how you define the determinant of 2 cross 2 matrix. And similarly, we can talk about the determinant of 3 cross 3 matrix. Okay, so for 3 cross 3 matrix, then probably I have to go to the general symbol for matrices. So this is 1, 1, this is 1, 2, this is 1, 3, this is
2, 1, 2, 2.
So what is the use of calculating the determinant of any matrix?
Sorry, what is the
use to calculate determinant of any matrix?
Okay, so the thing is, okay, so first of all, determinant has a lot of use, and one of the probably the easiest use is basically it will give you area, volume, like in basically if you do in if you are dealing determinant of two-dimensional object, then certainly it will give you area. If you are dealing with more than two-dimensional thing, then certainly it will give you the volume. Okay, so that is one of the use of determinant that certainly you can understand. But apart from that, actually it has a lot of connection with linear transformation. Okay, so once you go to the concept of linear transformation, that you'll see in the upcoming weeks, so then probably you can appreciate it more. Like from the determinant, actually you can get a lot about, so basically you can get so many things about a linear transformation. So you can say whether the linear transformation is 1, 1, or whether the linear transformation is onto. Okay, and you can find the eigenvalue of a linear transformation. Okay, so there are so many things actually you can later you will see why this determinant is so useful. But okay, so one of the easiest thing that you can do with the determinant is you can find area and volumes. Okay. So so how we define? So first, what we have to do is basically, okay, you don't have to remember. once you remember the determinant of 2 cross 2 matrix, then basically you don't have to remember of determinant of any matrix of further order. Okay, so what basically you have to do, you have to take this matrix A1, 1, and you have to multiply with determinant of this 2 cross 2 matrix. Okay. So you ignore this part, you ignore this part, and you ignore this part. So you have to A11 times determinant of this matrix, the sub matrix. Okay, what is the determinant of this sub matrix?
A22 into A33 minus A32.
Correct. Okay, sorry. Right. So the next thing is again, so for basically, okay, so you'll maybe you know, like since this you have 1, 2, and if you are add actually 1 plus 2, you will get 3. 3 is an odd number. Okay, so that's why you are getting you will get a negative sign here. Okay, A1, 2. Okay, so once you have A1, 2, okay, so then what basically you have to do,
First row and second column should be ignored.
so you need to ignore the first column, sorry, first row and the second column. Okay, so basically you have to take the determinant of this matrix, this one, and you form a matrix by taking this A21, A23, A31, A33. Okay, so you have to multiply A12 with the determinant of this matrix. And what is the determinant of this matrix?
A21 into A33 minus A23 into A31.
Yeah. So okay, so again, like you can say A21 to 33, but okay, this is not the correct way to say it. Like it's you should,
2, 1, 2, 1.
Yeah.
Got it.
Yes. I'm saying decimals. T1.
Yeah, got it. That is the ijth position.
Yes. So that is why. So the next is A13. So as you can see, A13, if you add actually 1 plus 3, you will get an even number. Okay, so that's why you don't have negative sign in place of A13. So as you can see here, if you add 1 plus 1, you will get 2. That's why here you have positive coefficient of A1. But if you add 2 plus 1, you will get 3. So that's why you have a negative sign. So for 1, 3, what you have to do, you have to ignore the first row and third column. So basically you have to take the determinant of this matrix. Okay. So this is 2, 1, A32 minus A22, A3. Okay, so this is how you compute the determinant of third cross matrix. And in the same way, actually, you can compute the determinant of any matrix of n cross n order. Okay, probably for 4 cross 4 you can compute, but it's really difficult to compute a determinant of a matrix of order 5 cross 5 and above. Okay, so it will take too much time for you to compute determinant of 5 cross 5 matrix or maybe 6 cross 6 matrix. So it's more or less easy to find the determinant of a matrix up to order 4. So any doubt till now?
No, sir.
No, sir.
Yes. Okay, so in this way you can compute the determinant. So
Sir, I have an example for you, sir. Sir, can you represent matrix in exactly?
okay, so I can't hear you. Just a minute, let me mute all of you and you can unmute yourself and you can ask the question again.
Hello, I'm audible, sir.
Yes.
Sir, can we represent a matrix in an alternate way, like a graphical representation, something like that?
No. So can one of you tell me what basically he is asking? It's not audible for me.
No, it is not clear, sir. Actually, some background voice is.
Yes, probably. Yeah. Okay, so one of the crucial property of determinant is basically it's multiplicative. Okay, so this is really useful for many application. That is you can write matrix, but certainly you have to slightly modify it. Okay, you can see a matrix, for example. So the question basically he asked in the chat box, can we represent matrix in some graphical representation? So the thing is, what basically I can do, if I have a matrix of like this 1 2 2 4, then what basically I can do, I can think this matrix as a tuple. Okay, 1 2 2 4, and I can think this inside R4. Okay, so the thing is, you have to slightly modify it. Okay, so you have to slightly modify it to think this matrix as a element of some Rn. Okay, then only you can geometrically you can say, okay, so this matrix is somewhere inside Rn. Okay, otherwise I don't think there is any graphical representation of a matrix.
So like you said it as a tuple, can we assume it to be like array or like a list or an array?
Array. So the thing is, okay, so this is more or less a array. So in array you have a order, right? So as a array, these two things are different, right? 1 2 2 1, right? Whether they are different as a array.
No.
So array is basically it's a collection of numbers, right? With some order.
Right, sir.
Actually, these two are different, sir. In the
Yes.
position, the order is different. So
Yes.
in array also, these are two different arrays.
Yeah, that is what I'm saying. So in array, these two things are different, right? So that means you can say that this is also a array. Okay, no problem.
No, I mean, sir, what you have listed is as a list, like 1 and 2 and 2 and 1 is I'm assuming them it to be as a list, but 1 2 and 2 4, the matrix I'm assuming it to be an array, like 0 0, then a 0 1 location, then 1 1 1 location, like that way.
No,
am I
sorry,
wrong?
Sorry, can you repeat? Like, it's not clear to me, like what you said.
Sir, what I'm saying is that the matrix I'm assuming it to be a 2 by 2 array. We can assume it that way, right? I mean, instead of taking it as separate rows.
No, that certainly you can do. So the thing is, what basically I'm saying, so he actually, the question he asked, like whether can you see a matrix as some geometrical object. Okay, so that is what I'm saying. So the thing is, if you want to see this matrix as some geometrical object, then directly you cannot see it. So first thing is, you can write this matrix in this form. Okay, then this certainly this number is somewhere in 4-dimensional plane. Okay, then only I can see this.
Okay, so we can take it as tuple or an array or a list. We can
Yeah.
anyway.
So it's
Okay.
It's depend basically it's depend what basically you want to do. Okay, with that matrix. So if you want to see as maybe if you want to see as what, like some geometrical object, then probably you can see it as a tuple and you can see something inside R4. And probably if you want to see you want to store this matrix for a programming, then probably you can store it as an array. Okay, so it's not issue. Okay, so it's depend on your basically what you want to do with that matrix. Okay.
Okay, okay.
Okay, so yeah, so I guess determinant. So this determinant part is clear. And next thing, what I wanted to say that determinant is multiplicative. Okay, so this is really crucial. So what is the meaning that the determinant is multiplicative? So if I take two matrices A comma B, and I suppose I assume that both are square matrix, okay, because then only I can talk about their determinant. So suppose both are square matrix of order n cross n. Okay, since both are square matrix of order n cross n, then I can multiply both the matrices A. So I can multiply both the matrices and I'll get a matrix which I denote as AB. So determinant of, so this is really important. Determinant of AB is basically determinant of A times determinant of B. So basically what it says, if I know the determinant of A, if I know determinant of B, then I don't have to compute the determinant of AB separately. Okay, I just multiply determinant of A and determinant of B, then automatically this will give me the determinant of AB. Okay, so one of the obvious, okay, not obvious, but
So,
one of the is.
Sir, but here, but the other way around, it's not true, I think.
But what do you mean by other way around?
Determinant of A into determinant of B is not always equal to determinant of AB.
No, that is what I have written here. They are same, right?
No, sir. Actually, if we take A to be a 3 cross 3 and B to a 2 cross 2 matrix, then determinant of AB is not defined at that case.
No, that is determinant of AB is not defined. So you see my condition. What is the condition I have taken?
That is, sorry to interrupt, sir. That is actually matrix multiplication, right? AB is not equal to BA. So
there, the matrix multiplication is not well defined, right?
Yeah, that's what AB will not be equal to BA, right, sir?
No, it's AB has no meaning. Okay, so the matrix multiplication itself is not defined. Okay, so as I said, when you can multiply two matrices, if the number of columns of the first matrix is same as the number of rows of the second matrix, right?
Yes, sir. I'm talking about 3 by 3 matrix only. If we take the same, I mean, any A, for the matter of any matrix A and matrix B, let it be a square matrix itself. When we multiply A by B, it will, and then we reverse and put it, let us multiply putting B as first and then putting A as second. The answer will not be the same, right? No, sir. That's what I'm asking.
AB, so AB is may not be equal to B.
Yeah.
Yeah. No, that is something different. He is saying something different. Okay, so basically what he's saying that so that basically what he is saying, suppose I take a matrix A. So suppose A is a matrix 2 cross 2 matrix, right? And B is a 3 cross 3 matrix, right? So what I can do, I can compute the determinant of A, right? Correct. I can compute the determinant of A. I have a method of doing that, and similarly I can compute the determinant of B. Okay. So what basically he's saying that determinant, so in this case determinant of A times determinant of B is not equal to determinant of AB. See, the problem is, so here this A times B has no meaning. So in this case, this A cross B has no meaning.
Yes, sir.
So then if this A cross B is not a matrix, then I cannot talk about its determinant. Okay, to talk about the determinant of A cross B, first it has to be a square matrix. Okay, certainly here A cross B is nothing. It's a completely meaningless object. So then certainly I cannot talk about the determinant of A cross B. Okay, so what? So as you can see here, I have an assumption, right? I have an assumption that A cross B, both are square matrix of same order. Okay, so that means if A is 2 cross 2 matrix, then B has to be 2 cross 2 matrix.
Yes, sir.
If A is a
So
3,
that we can say that AB is not equal to BA in this case, but determinant of AB is equal to determinant of BA.
where? So in this case, you are talking about this case.
Yeah.
Yeah. Here. So matrix multiplication in general is not commutative. Okay, so determinant. Similarly, you can say that determinant of BA. Determinant of BA is determinant of B.
AB, yeah.
Determinant of. So determinant of AB and determinant of BA, they are same. But certainly you cannot say that AB is same as B.
Yes, sir.
They
may be same, but
yeah,
not
maybe
always.
so this may not hold.
Yes, sir. Okay.
Yeah. Any doubt?
No, sir.
Yeah. So okay, so this is probably the okay. So one of the consequence of this result is basically, suppose you have a matrix A. Since I have not discussed about inverse, okay, so the inverse matrix is basically is a matrix. Suppose you have a matrix A of order n cross n. So A inverse is basically is a matrix such that it satisfies this condition. Times A is basically identity. This is the identity matrix of order n plus. Okay. So that is,
sir, repeat, sir.
so inverse of a matrix A is a matrix. So this is a new matrix, and we call this matrix as inverse of A. And this is a matrix with this property. So this is a new matrix which satisfies this condition. If you multiply A inverse with A, you will get a matrix, identity matrix of order n cross n. For example, if I take a matrix A, B, C, D, this is my A. So A inverse is some 2 cross 2 matrix, right? A inverse is some 2 cross 2 matrix. You will see how to find A inverse, but now for timing, you think A inverse is a matrix such that if I multiply A times A inverse, and if I multiply A inverse times A, I will get square matrix, identity matrix of order. Okay. That is basically the inverse matrix. So inverse matrix is a matrix which satisfies this condition. Okay.
So this is only applicable for n cross n matrix.
Correct, because so inverse, actually we can only talk about square matrices. Okay. And also one more condition is that the determinant of the matrices has to be non-zero. Okay, otherwise it's not possible to find a inverse of a matrix. Okay. So suppose,
sir, suppose we have suppose we have AB is something which is not an identity matrix, and AB is equal to BA. Then it's not possible, I think. AB should not be equal to BA in this case.
No, that is possible. Maybe like you can take some scalar matrix.
Sir, but how? Because A into A inverse is equal to A inverse into A is equal
okay,
to
I'll come that you try to think, you take A to be in some matrix and B to be some scalar matrix. You try to take B as a scalar matrix, then you will see that A times some scalar matrix is not identity, but again, scalar matrix actually commutes with every other matrices. Okay, so I'll come to that in the end.
Oh, okay. Okay.
So the thing is, what is the property of inverse matrix? That is basically it satisfies this condition. If A is basically this condition, A is a matrix of order n, then A inverse satisfies this condition. So this is basically matrix multiplication. I'm multiplying A with A inverse and I am getting identity matrix. So now if I take the determinant of the both the things, what is the determinant of identity matrix of order n cross n?
1.
One, sir.
This is 1. So if I simplify this, what I will get?
Determinant of A into A inverse
1 upon
is equal to 1.
1. That means determinant of A inverse is what?
Reciprocal of determinant of A.
Basically 1 by determinant of. So basically using this property of determinant, what I can tell, once I know the determinant of A, I can tell you about the determinant of A inverse and vice versa. So once I know determinant of A inverse, I can tell about the determinant of the matrix. And if I know determinant of the matrix, then I can give the determinant of A inverse. Okay, so I don't have to compute both the things separately. Okay, once I know one thing, I can tell about others. Okay, clear? Like, okay, so you'll see probably how to find the inverse of a matrix in the next week. But okay, one of the consequence of this property is basically this one. Like if you know the determinant of a matrix, you can tell about the determinant of its inverse. And if you know the determinant of the inverse, then you can talk about determinant of the matrix. Okay.
Sir, if we write -1 above the bracket,
Sorry?
If we write -1 above the bracket, means determinant of A and bracket and above.
This is a symbol to represent this A inverse. Is basically it's a symbol to represent the inverse of a matrix. Okay, this is just a symbol. Okay, so there is minus sign is basically just a symbol. Okay, don't take the literal meaning. Don't think this as 1 by A. Okay, don't think this this A inverse as 1 by A. Okay, so A inverse is a matrix. Okay, this is a symbol. Okay, so instead of if you don't like this A inverse, you simply write it as B. Okay, so instead of A inverse, you simply write it as determinant of B, and B is basically inverse of A. Okay, so this is a symbol. Okay, don't think, see, 3 inverse is something different, 1 by 3. Okay, so here A is not 3, it's a matrix. So A inverse is a symbol. Okay, don't think this as 1 by A. Okay. You will see later. Yeah.
Means if I write -1 above the bracket, then will it have a different meaning or not?
No, it's not clear to me what you are saying.
If I write -1.
As I said, no, this is, don't think as it's a symbol. I'm representing the inverse matrix using this symbol.
Okay, sir.
Okay, this is just a symbol. Don't think, don't take the literal meaning that 1 inverse. See, the thing is 1 by 3 has a meaning. Okay, 1 by 3 has a meaning. But if I write 1 by maybe say Ram, this has no meaning. Okay, because Ram is not a number. Okay, so when I'm saying in inverse, don't think as 1 by A, because here A is not a number, it's a matrix. So this has no meaning. You have to define something for that. Okay, then only you say, okay, this has some meaning. Until unless this has no meaning.
Okay, sir. Got it.
Yeah. Okay, so so the next thing is probably once I have determinant, then probably I can talk about minor and cofactor. Okay. So suppose.
Excuse me, sir.
Yes.
Sorry to interrupt, sir.
Hmm.
Actually, A inverse and A transpose both are same, no, sir?
No. They are completely different. So.
Okay. Transpose is just reversing the order, rows
yes.
into columns.
Yes.
But A
correct.
inverse is this formula, 1 by determinant of A into.
See, transpose actually you can talk about transpose of any matrix. Any matrix. It's not that it has to be a square matrix, right? Transpose you can talk about any matrix, right?
Okay.
You can take a transpose of 2 cross 3 matrix, 5 cross 7 matrix, 10 cross 1 matrix. Okay, you can take transpose of all these matrices, but you cannot take determinant of all these matrices. For determinant, you need a square matrix. Okay.
So transpose is only for matrix, not for determinant.
Transpose you can always take for any matrices. Okay, for determinant you cannot take for any matrices. Determinant you can take determinant only for square matrices. Okay.
Okay, sir.
And for square matrices, determinant and transpose, they are completely different.
Okay, okay, sir.
Yes.
Okay, thank you, sir. Thank you.
Yes. So, okay, so let me discuss minor and cofactor. You'll again, like you'll see more about determinants in the next week. Okay, so how? Sorry, not determinant. This inverse. How to compute the inverse of a matrix in the next week. Minor and cofactor. Okay, so once you know how to compute minor, then cofactor more or less comes free. Okay, so the only thing you need to do, you need to know how to compute minor of a square matrix. So only this minor and cofactor concept exists for a square matrix. Okay, for non-square matrix, there is no concept of minor and cofactor. So suppose A, so if A is a n cross n matrix, okay, suppose A is a n cross n matrix, and then, so if A is a n cross n matrix, then the minor of the I, jth entry is basically, then the minor of this is basically is the determinant of the submatrix formed by deleting the ith row and jth column. So basically what it's saying, suppose you have a matrix A, B, C, D, E, F, let's say G, H, I. So this is a 3 cross 3 matrix. Okay, obviously this minors and cofactor, I can only talk about square matrix. Okay, so suppose I want to compute the minor of this E, this 2, 2th entry. 2, 2th entry. So what is the minor of 2, 2? What to compute the minor of 2, 2? What I have to do? I have to delete the
second row and second column.
Second row
and second column.
So if I delete this, then I will get a new matrix. A matrix whose order is 1 less than
AC GI, sir.
Yes, correct. Yeah. So SC GI. So determinant of this matrix, whatever this matrix, determinant of this matrix is precisely minor of I comma this 2 comma 2. Okay, and suppose if I want to talk about the let's say I want to talk about the minor of this one, F. So this is what? This is 2 comma 3, right? So for that, what I have to do?
Second row and third column should be deleted.
So I have to omit.
Drop second row and third column.
Correct. I have to omit the second row and the third column. Okay. So then I will get a matrix of order 2 cross 2. And what is that matrix? AB,
GH.
GH. Okay. And determinant of this matrix is basically
the minor for
2
comma 3.
2 comma 3 entry of this matrix, that is F. Okay. And this is how you compute the minor. Okay, and once you compute the minor, then cofactor is more or less computing cofactor is more or less
coefficient or cofactor
is easy. So what basically you have to do? So if you see, so with respect to this F, so by omitting the rows and column, you are getting a matrix, right? You are getting a matrix. Now what we have to do for the cofactor, what you have to do? You have to just multiply -1 times
I plus j
2 plus 3. For particularly for this F, I'm talking about this F, because F is basically 2/3 entry, right? So instead of 2/3, you have a ij. If the element is in the ijth place, then the cofactor of that element is basically -1 times I plus j into the minor. Is it clear? The definition clear? I'll take an example and I'll compute everything. Okay, so my first concern is whether this definition is clear, how we are computing minor and cofactor.
It's clear, sir.
Okay, so let me take one example and I'll do it. So let me take 1, 0, 1, 2, 1, 0, 0, 1, 1. Okay. So first thing I have to compute 1, 1th minor, right? So this is I want to do. So first what I have to do, I have to omit the first column and first row, right?
Sir.
Correct. So I have to
Yes,
omit this one, and I have to omit this one, right? So the minor is basically what? Determinant of this matrix, correct?
Yes, sir.
1 0 1 1.
1, sir, actually.
So
The
this is
value is 1.
So minor is 1.
1.
Right? This is the minor. And what is the cofactor?
-1 of.
So this is, I have to check in which place this entry is. This is 1, 1th place, right? Right?
Yes, sir.
So the cofactor is -1 power
2.
1 plus 1 times the minor. What is minor here? 1.
1.
So if I multiply, I'll get 1. Correct?
Yes, sir.
So next I have to, okay, let me take maybe 2, 3, let me do 2, 3 entry and compute the minors. Let me take 2/1. What is the 2/1 minor? So this is the
No, sir, that is.
Sorry. Yeah, correct.
Yes, sir.
Yeah,
2 is to 1.
Mhm. So this is the 2-1th entry, right?
Yes, sir.
So what I have to do? I have to omit the second
row in first column
and first column. So if I omit the second row and the first column, I'll get a matrix. What is that matrix?
0
Zero,
1 1 1.
0 1 1 1.
1 1, right?
The
And
determinant is -1.
determinant is
-1.
minus
-1.
minus 1. Okay. And what about the cofactor?
Minus
Plus
1.
1, sir, actually.
plus
-1 of 2
plus
plus 1.
-1.
Minus 1 power 2 plus 1 times the minor. So
Minus
minor
1.
minor is
1 into
minus
-1 is
Plus
1.
1.
This is basically -1 times
1.
-1, which is 1. Okay. Clear?
Yes, sir.
Okay, let me take maybe
Yes.
one more example. Let me take this entry, this 3,3 entry. So if I take this 3,3, then what I have to do? I have to omit this
Column this row.
and
Third.
this the third column and the third row. So then I'm left with this matrix 1 0
0 2.
2 1 1 0 2 1. And what is the determinant of this matrix?
1, sir.
1.
1. And similarly, I can compute the cofactor. And how I compute? The same process.
-1 to the power of 6.
3 plus 3.
Times my
Times
minor,
1.
which is basically 1.
1.
Okay, so this is minor. This is how you compute minor and cofactor of a matrix. So once you compute the minor, then basically for cofactor, you have to check in which position basically this entry is. Okay, once you know the position, then you take -1 time power I plus j. So if the position is basically I plus j, you take -1 times -1 power I plus j times your minor. That will give you the cofactor. Okay. Okay, so now I guess I'll take your questions. Like if you have any doubt, then I will start explaining all this.
Yes, sir. Actually, can you please explain a system of linear equation? I mean, with some examples, sir. Unique and infinite solutions. No solution.
Okay, so the thing is, I'll suggest because in this week actually you don't have actually a system of linear equation. You have only the formation of system linear equation, and once you have a system of linear equation, how you can construct the associate matrix. Okay, so in week 2 you will learn more about solving system of linear equation.
Okay, sir.
So so now for the timing, now you try to remember that if you have a system of linear equation, then that particular system of linear equation can have 3 possible solutions. Okay, either this system equation will have no solution, or and the second thing is it can have single
Unique
solution. Yeah,
solution.
unique solution. And third condition is it can have infinitely many solutions. Okay, solving system of linear equation you will see in week 2. Okay.
Okay, sir. Little bit confused. Okay, sir. We will see next week, sir.
Yeah. No, is there any question like from, because most in if you see the activity part, then there actually we didn't ask you any question like particular question to solve it. We didn't give you any system of linear equation, and we did ask you to solve that system of linear equation.
Sir, but it is given where to find out whether there is any solution,
unique,
infinite solution, or many solutions.
Sometimes will be correct, sir. Sometimes I will be wrong, sir.
There
So
are
little
2
bit
parallel
confused.
lines, then it is supposed to be no solution, and 3 conditions has been given to us.
Can you tell me which question number you are talking about?
Yes, sir. Practice assignment. In that question number 1 had question saying that whether it is infinitely many solutions or no solutions or any unique solution.
Which one?
Practice assignment question number 1, sir.
No, practice assignment.
Week 1.
Week 1 activity,
Yes, sir.
which, okay, practice assignment we are talking about.
Yes, sir.
So, okay, so the graphs are given, right?
Graphs
Yes, sir,
also
we
given,
graph-
sir. And we have to find the solutions also, sir.
See,
No
Then only we are able to
solutions.
match.
so for that, okay, so these are all straight lines, right?
Mm.
So straight line you have studied in maths 1, right?
Yes, sir.
So when two straight line will intersect?
Only unique solution.
No. That is what I am saying. When two straight line will intersect? If they have different slope, right?
Okay.
Okay.
Correct. If they have different slope, if they have same slope, then basically they are parallel, right?
Okay,
Yes,
sir.
sir. Yes, sir.
So that means they will never intersect. Okay. If they are not parallel, that means they have different slope, then certainly they will intersect, right?
Sure.
So for straight line, you can easily compute the point of intersection, right? So that is that certainly you don't need anything from maths to basically you can you just need to solve two straight line, like that is more or less you can do
Like calculating the slope alone is
enough. Like you don't have to solve it. Yeah. So once you know the slope, okay, if the slope are same, then not blindly, certainly you can directly you can say that they will never intersect. So no solution. No solution.
No solution.
Yes. And to draw the straight line, what you need to do, you just need to find out 2 points of that straight line, right?
Yes.
So
Yeah.
once you find 2 points of that straight line, you can easily draw it, right?
Okay.
So basically what you need to do, you need to check the slope and you need to find out 2 points of the straight line. So once you know all these 2 information, then certainly you can solve the question number 1, right?
Okay. Sure.
Okay, sir.
Yeah.
Hello, sir. Activity question 1.3, question number 3. The third and fourth option. I could not solve.
Sorry. Okay. Activity
1.3.
1.3.
Question 3.
Oh, so what is the issue?
Third and fourth option. How to approach means, how to think for it means.
Okay, so it's so the third option says that okay, just a minute. Let me take a screenshot. So third option basically says you have a system of linear equation, right? This is the system of linear equation, right? And it says this equation has a solution. Has a solution, right? Then it's asking whether this equation has a solution or not, right? This is your question. This is the third option, right?
Yes.
Right. So so first let think this as some 2 cross A is a 2 cross 2 matrix. Let think this as a 2 cross 2 matrix. A B C D and x1 and x2, which is B1 and B2. Okay, so saying this has a solution, that means it has some solution. Let's say alpha beta, right? This is a solution of this system. So next question is saying whether this equation has a solution or not. What? This equation C times Okay, let me change this C to some number. Let's
X,
say,
Y, Z, sir.
sorry.
A. X, Y, Z.
No. I C is a scalar, so I cannot. Let me take M.
Okay.
So what I want. So basically, it's saying whether this equation M times A. That means what? MA, MB, MC,
MD.
MD. Whether this equation has a solution or not. Now, can you guess whether this equation has a solution or not? So
it has.
Alpha, this is a solution of this equation, right? Now, if you take, instead of alpha beta, if you take alpha by M and beta by M, now can you tell, now can you check whether this is a solution of this equation or not?
No, sir, I'm not getting.
Sorry?
No, I'm not getting.
No, what I'm saying, so what, first tell me what is the meaning that this is a solution of this system? What is the meaning that this is a solution of this system?
LHS is equal to RHS.
No. Okay, just whoever asking that question, I'm asking to her. Okay, so what do you mean by this is the solution of this system?
If we put alpha or beta in place of x1 and x2, then LHS is equal to RHS.
Okay. So then you will get a equality, right?
Yes.
So now we want to find some x1 and x2 such that if I substitute here in place of x1 and x2, I should get a equality, right?
Yes.
Right. So what I'm saying, so you try with this one. So in place of x1 and x2, you try with alpha by M and beta by M. Right. You try in place of x1 and xm, try with alpha by M and beta by M. You try to multiply this matrix with this one, and you see whether you are getting B1 and B2 or not. Because see, this certainly implies.
Sir, but why alpha by M and why you have taken alpha by M and beta by M?
Because see, because I'm multiplying M here. Okay. In the matrix. So if you see what actually I'm doing, I'm multiplying M here. Okay. So I somehow I'm getting some extra M in the above, right? So if I multiply, so I'm getting some extra M above, right? So I have to cancel it. So for that I have to divide one M, right? In the solution.
Divide the X with the same. Yeah.
Correct. Yes, that is what I'm doing. So if I divide this M in the solution, then that M and this M, they will get cancelled, right? So eventually I'll get D. That is the main idea. So what okay, let me multiply these two things. If I multiply, what I will get? I multiply this one, what I will get? Tell me what I will get.
MA into alpha by M plus MB into beta by M.
So what is that? That is basically A alpha.
Yes.
Plus B beta, right?
But sir, in question, means here only M is multiplied with ABCD, not with alpha and beta. Why are you taking?
Sorry?
Dividing. You are in question, M into A is given. And then why are you dividing M and by alpha and beta?
Because A is fixed, right? I can only change X. So I need to find X. So only thing I can change is basically X. I cannot change A. Okay, A is fixed. M is fixed. Okay, I have to find X so that this thing holds, right? Is it clear? So no. So the thing is, okay, so this is a solution means what? This is basically A alpha plus B beta is B1. Okay. C alpha plus D beta is B2. So that this one you know. Okay, this one you know. Now you have to find some x1 and x2 such that this condition holds. Now if I slightly modify and if I take x1 to be alpha by m and x2 to be beta by m, and if you see, if I multiply this thing, what I am getting a alpha plus b beta plus c alpha plus d beta. And previously I already know that this a alpha plus b beta is b1 and c alpha plus d beta is b2. So basically then I am getting this beta 1 and beta 2. That means this equation holds. That means this is a solution. So since the main trick is basically, since I am multiplying m over here, then I have to divide a m over here. Then only I will get the solution. Previous thing. So the main idea is you try to find a solution. You take a solution for this equation and you try to slightly modify it so that you will get a solution of the next equation.
Okay, sir. Got it.
Yes.
Hello, sir. So can you please provide the solution period of practice assignment, sir?
Yeah, we'll give you, like maybe it's Friday. Okay, I don't know the exact date, but we'll give you. Okay, like before the deadline of graded assignment, certainly will.
Okay, sir.
Sir, will this slide be shared, sir?
Yes, I'll share this slide.
Hello, sir.
Yes.
Sir, I have a doubt in practice assignment question number 2, option 3.
Sir, we have covered all the concept.
Question number 2.
Option 3.
What is the doubt?
Sir, in the second matrix, I get the 2 raised to power 10 common, but I didn't get the 10 in the second matrix where it's come.
No, you multiply A with 10 times. Multiply A. So, okay. So, this is your matrix, right? 2, 2, 0, 2, right? This is the matrix?
Yes, sir.
So this is actually, you can prove it basically in method of induction. So suppose you take A times A. What is A times A? What is A times A?
We have to multiply. Sir,
Yeah.
can we do it like this? We take 2 from the first row common and 2 from second row common. Then we can.
Correct. That is also possible. Yeah, you can do it.
But I think we cannot take 2 times 2 as common because it's matrix. You can take only 2 as common. Then
no. Basically, what you have to do, you have to take 2 common from all the entries. I'm saying, not from the row and column. Okay. So
okay, sir.
what you can do, you can write this A as, so this you can write as 2 times 1, 1, 0, 1.
1.
Yes.
Then we can multiply with the same.
Yeah, we can. Then you can do the same thing. You can multiply. So the thing is, you have to. So first you have to check a pattern. Okay. First you try to multiply A with A. Then you try to multiply A times A times A. Okay. And see what pattern actually it's following. Okay. So then similarly you can see like. So this, for this particular type of question, you need some method that is actually induction. Okay. So
okay, sir.
Using induction, you can do it. Otherwise, you can try to. So certainly, I will not suggest you to multiply out this matrix 10 times. You try multiply A times A, and you see whether A times A is coming like this or not. That is 2 power 2. 1, 2, 0, 1. Okay. Then you see whether this is coming like this or not. 2, 3, 1, 3,
1,
3,
0,
0,
1.
1. And if certainly if this holds for 1, 2, then most like 1, 2, 3, then most likely it will hold for 10 also. If you multiply.
Okay, sir.
So that is actually the main idea. It's not, so we didn't ask this question so that you will multiply this matrix for 10 times. You try to do it for 2, 3 times, then you see, check the pattern, and similarly you can say that, okay, this will hold for 10 also.
Okay, sir. Got it.
Sir, in practice assignment question number 6.
Yes. What is the issue here?
I cannot form that matrix actually.
No, you don't have to form that matrix. So you, if you know, like if you add multiples of a row to some another row, okay,
Okay.
then do you know that this will not change the determinant of the matrix?
Yes, yes.
Then certainly, then what you can get, so then you can tell that determinant of B is same as determinant of A.
Okay, okay.
So once you know, so basically how you are forming B. B is a matrix obtained by adding 5 times first row of A to the third row of A. So that means determinant of B is same as determinant of A. Okay. So once you know that determinant of B is determinant of A, then you can compute, right?
Yes, yes, yes.
Any other doubts?
Hello, sir. Actually, 1.2, question number 8, last option I could not get.
1.2?
Question number 8, and in that last option.
Okay, so this is a tricky one. Okay, so let me do it. So basically, question number, okay, whatever. 1.1.2, question number 8, option 4.
Sir, last option.
Okay, is there no hand raised order followed? Okay, so the thing is I can't see, like, so that is the problem. Every time I have to go and check. It's better if you directly ask the question.
Sir.
Just a minute, let me complete this one. Question number 1.2, question number 8, option 4.
Last option.
Yeah, option 4. Okay, so basically it's saying, well, whether there is any real matrix A such that, is there any real matrix with this condition? A square plus A plus identity matrix is 0, right? This is the question, right? 2 plus 2 real matrix.
Yes.
So, okay, so let me take some arbitrary real matrix A. Right. So I want to find a matrix A that satisfies this condition, real matrix, obviously, not complex matrix. I want to find a real matrix which satisfies this condition. So let's start with some arbitrary matrix A, B, C, D. Right. So now if I multiply A with A, what is A square? What is A square? A square is what? What is the first entry of A square?
A square plus B into C.
A square plus BC.
Yes, correct. And whatever the 1, 2, 2th entry of this A square, this is probably a D, sorry, a B plus BD, right? And the 2, 1 entry is SC plus DC, right? And if you compute, then you will get BC plus D square. Just a minute. Let me. Yeah. So this is the matrix A square. So now what I will do, I will add A square plus A plus identity. So what I will get if I add all these things, then what I will get, A square. Please mute yourself. I'm getting some noise. Plus 1, right? This is a B plus BD plus B.
Plus 1.
No, here, so here I in I, that will not, so
0.
in 0 in 1, 2 position of identity matrix is basically 0. This is C. This is B, C plus D square plus D plus 1. Okay. So I want this to be 0, right?
Yes.
Okay. So I want this to be 0. So then, so if I equate, what I will get A square
Plus BC
BC
plus A plus 1
is
plus
0, right?
Yeah.
Similarly, AB plus BD plus D equal to 0. Then SC
plus B.
BD plus B. In second, BD plus
BB.
BD plus B.
Second row, sir.
correct?
So second equation AB BD plus B equal to 0.
AB plus BD plus D. Yeah.
This one is fine, right? SC plus DC plus C.
Yes, sir.
Yeah. Then you have BC plus D square plus D plus 1 equal to 0, right? So these are the 4 equations you are getting. Certainly these are not linear equations, so it's slightly difficult to solve the system of this equation. So more or less we need to do it by trial and error. So first thing, from these two equations, if you see, I can take common, right? B times A plus D
Plus 1.
1 equal to 0. And from here, so certainly from the first and the fourth equation, I can't take any common. Okay, because you have 1 in the end. So here I can take
Hello,
C.
sir.
Yes.
Sir, actually, I find some matrix just by arbitrarity. I mean, sir, actually what I found was I took a matrix 0, 1, -1, and 1.
Yeah, that may work, but I'm basically explaining like how you should do it. Like how yeah. So how you should approach this type of question. Like you can pick a lot of matrices and you can check whether they satisfy this condition or not. But in general, how you should approach this type of questions. So as you can see, so from here I can conclude that either B is 0 or this part is 0, right?
A plus B equal to -1.
So if B is 0, suppose if B is 0, then this equation will become what?
A square plus 1
equal to 0. Whether this equation has some real solution?
No, sir, imaginary solution.
So then certainly you will not get a real matrix, right? But we want a real matrix, right? So then B cannot be 0, right? Is it clear till now that why B cannot be 0?
Yes.
So that means A plus
B equal to -1.
Equal to 0. right? And similarly, you can check that C also cannot be 0. If C is 0, right, then this will become what? D square
plus
D
plus 1 equal to 0.
And this then you will get a complex solution for D, but we don't want any complex solution. So similarly, C cannot be 0 and B cannot be 0. So what we have? We have A equal to minus D minus 1, right?
Yes.
Correct?
Yes.
So now we can actually take some number. Let's say take a number which two numbers A and D such that they satisfy this condition. Let's say take A to be 1. Then what will be the value of D?
-2.
D is -2, right? So if I take A to be 1, then D to be -2. Now you substitute the value of A in your first equation. What you will get?
1 plus BC plus 1 plus 1.
BC is equal to -3.
So that means BC equal to -3, right?
Yeah.
And if you substitute D here, then what is D equal to -2 here? What you will get?
BC plus 4 -2 plus 1 equal to 0.
Yeah. So then here also you are getting BC equal to
3 -3.
-3. Okay. So we know, so somehow we have predicted some values of A equal to 1 and D equal to -2, and apart from I am getting BC equal to -3. So now we just need to predict some values, like not predict, we need to guess some values of B and C so that this satisfies this condition. Now you take, let's say you take B to be 1 and C to be -3.
We also can put it in second and third equation.
Which one?
The value of A and D.
Value of A and D.
Yes.
In second, that if you put in second and third equation, you will not get anything, right?
Yeah.
So now if you take this matrix, let's say this matrix, then most likely it will satisfy the condition. 1
-2.
No, D is
-1. Sir, how do we get one A and D from A equal to -D -1?
Sorry?
From A equal to -D -1, how can we?
No, we took some numbers, two numbers that satisfy this condition. That is what.
Just we are satisfying this equation.
Yeah, correct. You can try with others number and you can check whether that matrix will satisfy your original condition. Okay. So that is one way to solve this type of question. You try to simplify the expression as simpler as possible, and from there you can predict, you can guess some numbers, and you can try whether the final matrix will satisfy the condition. Is it clear, like at least how I am doing this question?
Yes.
Okay.
Means, sir, we can take any numbers or means what or a smaller number.
Yes.
It should be satisfied for any number.
Most likely it will satisfy by most of number. Certainly I cannot guarantee whether it will satisfy by all the numbers, but most likely it will satisfy by most of the numbers.
Means we should try with 1, 2 means small numbers. Right?
Yes, certainly. So for the first, if you are doing to simplify your calculation, like if you want to do less calculation, then certainly you should take less numbers. Okay, so then it will be easier for you to compute this one, right? If you take some smaller numbers, then it will be easier for you to compute this one, right?
Yes.
Because finally whatever matrix you are forming, okay, eventually for this matrix you have to check whether this matrix satisfies this condition or not, right? So if you take big numbers, then obviously it will be difficult for you to compute a square. Then you have to do more calculation. Okay, if you take small numbers, then obviously it will be easier for you to compute this one. Is it clear?
Yes, yes.
Okay.
Yes, sir.
Sir,
Yes.
Hello, sir. Hello,
Yes.
sir.
Yes.
Sir, actually, the practical assignment 1, I have attempted all the questions, but the score is showing as 0 only. It is not getting updated. I mean,
No, it will be updated after
the graded assignments are
graded
completed, sir.
Yeah. Once the deadline of graded assignment over, then
the
you
practical assignment score will also be displayed.
Yes.
Okay, sir. Thank you, sir.
Sir, can you explain one more time the practice assignment question number 6?
No, what basically I'm so the one of the property basically here what we are using, that if you add multiples of a row to some another row of a matrix, then certainly that will not change the determinant of the matrix. Okay, so in other words, for particularly for this question, the determinant so determinant of B is same as determinant of A. Okay, because how you are getting the matrix B basically you are getting by adding some row of A with some another row, some scalar multiple of another row of. Okay, that is how you are getting B. That means the determinant of B is same as determinant of B. So once that you know that determinant of A is same as determinant of A, so now you know that determinant of A is same as determinant of. So now once you know, then basically what you need to do, you need to find the determinant of 4A B inverse, right? 4A B inverse. What is this? So you know that if A is a matrix of order n cross n, then determinant of C power n times determinant of, right? So this is basically what A is a matrix of order 3, right?
4 power 3.
Yes, 4 power 3 into determinants of a B inverse, right? So this is nothing but 4 times 4 power 3 determinant of A into determinant of B inverse, right? And you know determinant of A into determinant of B inverse, that we have already proved, right? Determinant of a matrix inverse is same as determinant of
one by
determinant.
Yes. So basically by I'm using that property over here. Okay, property here. And one more thing, I know that determinant of A is same as determinant of B. So 4 times determinant of A into determinant of
A inverse.
A inverse. So this and this, they will cancel each other. So eventually you get 4 power. Clear?
Yes.
Yes, sir.
Okay, any other doubt?
Sir, can you explain, triangular matrix?
Yeah, so okay. So upper triangular matrix is a matrix basically where all the entries which are below the diagonal, they are 0, right? So if you are taking a square matrix, so upper triangular matrix is a square matrix. So first condition is it has to be square matrix, and all the entries which are below the diagonal, okay, below the diagonal, they are all 0. If this condition holds for a matrix, then only you call this matrix as a upper triangular matrix. For example, if I take this matrix 1, 2, 3, 0. So you see what are the elements which are below the diagonal. This is my diagonal, right? And here below it has only one element, which is 0. That means all the element below the diagonal, they are 0. That means this is a upper triangular matrix of order 2. And what about this matrix? 1, 2, 3, 0, 1, 2, 0, 0, 1. Now you go and see. You go and see what are the elements which are below the diagonal. So as you can see, below the diagonal, all the entries are 0. That means this is a upper triangular. So suppose in place of 0, if I write here 1, whether this is a upper triangular matrix?
No.
No, because here you have a non-zero element which is below the diagonal. Okay. So the only thing you need to check if all the entries below the diagonal are 0, then you say that matrix to be a upper triangular matrix. Okay. And determinant of a upper triangular matrix is basically the product of the diagonals. Okay. So for example, if you compute the determinant of this matrix, then this is basically the product of the diagonals. That is 1 times 1 times 1, which is 1. So the determinant of this matrix is 1 because I'm just multiplying all the elements of the diagonal. Okay. And similarly, determinant of this matrix is product of all the entries of the diagonal. This is 2. Okay. And same thing for lower triangular matrix. Okay. Lower triangular matrix is the elements which are above the diagonal as so all the elements above the diagonal should be 0. Okay, then you say that matrix to be lower triangular. Okay, for example, if you take this matrix, so instead of 0, 1, 0, 0, so you see all the entries which are above the diagonal. So this is the only entry above the diagonal and this is 0. That means this is a lower triangular matrix. This is
also a upper triangular matrix.
This is also a upper triangular matrix. Correct. Yeah. This is a lower triangular. And the same argument, as you said, you can also say that this is a lower triangular matrix, because if you see all the entries below the diagonal, they are also 0. So this is also a lower triangular matrix. So the definition is clear, like how you differentiate between any matrix and upper triangular matrix, right? Hello.
Yes, sir.
Okay. So any other doubt?
Sir, I have a doubt. Sir, suppose you take a matrix, 2 cross 2 matrix, A, B, and C, D, and we are doing this scalar multiplication. I mean, addition of a scalar multiplication of one row to another in this matrix. So if we just suppose this matrix has 2 rows,
So you have two. First thing is you have two matrices, right? A and B, correct?
No, sir. We have only one matrix.
Okay, so
I actually I want to check that the determinant is changed or not in the case which I will explain you.
no, can you tell me what basically what is your matrix and what you are doing? If you tell me,
sir, let's take a 3x3 matrix. Then row 2 is transformed by a times row 2 plus a times row 1.
Row 2
is transformed by
so row 2. So you are changing the row 2, and what is your so
row 2 plus a times row 1.
Row 2 plus a times row 1, right?
Yes, sir. Yes, sir.
So this is the property. So if you yes,
at the same time, row 1 is also get changed to row 1 plus b times row 2.
Row 1
plus b times row 2.
Row 2.
A and B might be same also. So here in this case, I think the determinant will be changed.
Yes, because the problem is what you are doing. You are operating this operation multiple times in a single step. Okay, you cannot you cannot apply this method multiple times in a single step. Okay, so you can do it in the next step. Okay, for example, what you can do. Okay,
yes, I can do row 1. Row 1 is transferred by
suppose this is this I'm taking some 2x2 matrix. Okay, let me same thing you have to do for. So first what I have to do, I have to replace row 2 by row 2 plus a row 1. Okay, so if I do, what I will get, I'll get 1 2 plus what I will get, a plus 1 plus 2a, right?
2a, yeah.
Okay. So now determinant of this matrix, okay, determinant of this matrix is same as determinant of this matrix. Okay.
Yes.
Next, what I have to do? Next, I will apply this one on this matrix. Okay. B row. So if I'll do, what I will get, let's say 1 plus a B and 2 plus B plus 2ab, right? And a.
Yes.
Now determinant of this matrix is same as determinant of this matrix, and determinant of this matrix also same as determinant of this. So what actually I'm doing, I'm doing this operation in multiple phases. Okay, I'm not doing all the operation in a single phase. Okay, if I do all the operation in a single phase, then that may give some different determinant. Okay, so all you have to do, you have to apply the method in different steps. Okay, and if you are applying in a single step, then probably you have to be very careful, like whether the final result, whatever result you are getting, whether you can get it using multiple steps by applying all this method once in a time. Okay, in that case, probably it will give you the same determinant. Otherwise, no. Okay. You apply both the step in a single phase, then certainly it will not give you. Most likely, it will not give you the same determinant.
We can apply it for a different row actually at the same time, but
yeah, you can apply. That is basically because you can. So that is. So you can, if you are applying in to a different row, that also you can get by applying the same thing multiple times, right?
Yes.
So whatever the final thing you are getting, if you get that final matrix by applying all these things single time, okay, then the final determinant will be same as the determinant of the original matrix.
Yes, sir. Yeah.
Okay. So any other doubt?
Sir,
Yeah,
practice question, sir, question number 8, sir.
Sorry?
Sir, practice question number 8. So just wanted to know how to frame that question, sir. Understand and also able to frame that question.
No, basically what you have to do, you have to write, you have to express this as a matrix form.
Exactly.
Sir, could you please share the slides?
Sorry?
Can you please share the slides?
Yeah, I'll share this slide. So, just a minute. Yeah, so you can see the question, right?
Yes.
So this question says a shopkeeper sells 3 types of clothes: shirt, jeans, and t-shirts in 3 different size: small, medium, large, in a week, and he sold 1 small, 1 medium, 2 large. Okay. So basically what you have to do now, you have to use some variable x, y, z, right? You have to use x, y, z for maybe shirt, jean, or t-shirt, right? So then you have to see how many shirts the shopkeeper sold and how many jeans the shopkeeper sold. So if the shopkeeper sold maybe okay, sorry, maybe I have to check. Let me see the main theme. What basically the shopkeeper is different size: small, medium, large. In a week he sold 1 small, 1 medium, 2 large size shirts. Okay, 2 small, 2 C medium, 6 large size jean, and 1 small, 1 medium, C minus 5 large size t-shirt. Okay, then the price of remains the same for different size, and large size t-shirt have the same price, and similarly small, medium size jeans have the same price. Okay, so the thing is, so you have three set of prices, right? Correct? You have 3 set of prices, right? So for the first one, you take that is as x. Okay. For the second one, you try to take as y, and for the third one, you try to take as z. Okay. Now you try to.
We are taking x, y, z for the shirts, jeans, and t-shirts. No?
Price, not
price.
Not for price. So see so what is the information it is given in the end? The shopkeeper on 727 43 rupees, right? For in a week for medium, small, medium, large clothes, right? So if you take this, let me share the screen. So if you take, so you have for a particular type, the price is x. For another particular type, the price is y, and for the another particular type, the price is z. Okay, so now you have to form a system of linear equation, that is maybe some combination, some ax plus by plus cj, which is 7, right? And another is 27, and another is 43. That means what? The shopkeeper sold a number of x items. Okay, the shopkeeper sold b number of y items, and the shopkeeper sold c number of z items. That means the total income is 7. Right. So similarly, so you have to see So for different category, different prices, you need to assign some variable. Okay, and then you have to see how many items the shopkeeper sold for that particular price. Okay, then the total price will be AX, and if the shopkeeper sold B number of items from this category, then the total cost will be BY. And if the shopkeeper sold C number of items, then the total cost will be CJ. So if you add, then you are getting 7. Okay. So basically, you need to form a system of linear equation by giving some variable to the prices. Is it clear? Like, so the thing is, I gave you some idea. Okay, I didn't solve the questions. Hello.
Not so clear.
Sorry.
Not so clear.
No, I am not saying about the question. Like what I am trying to say, I'm not giving you the answer of the question. Okay.
See, sir, here we are just making a linear equation. Okay, that AX plus BY plus CZ is equal to 7.
Yes.
So 7 is the amount that shopkeeper earned first after selling one product. Okay.
Small size product.
The small size product,
yes.
Whether it is a shirt, jeans, or t-shirts. Similarly for 27 and 43.
Correct. So see, the thing is, what is the, see, the price of small t-shirt, then another one is, I guess, shirt, right? And I guess jeans, right? All are same, right? Price of small t-shirt and shirt and jeans, they are same, correct or no?
Correct.
So you denote that price as X, right? How many small t-shirt the shopkeeper sold? Hello.
Yes, sir.
How many?
He sold one is small, one medium, and two large size. One is small.
One small, right? So price of small, similarly price of medium, the same thing. Price of medium t-shirt, shirt, and jeans, you denote it as Y. Okay. And price of large, you denote it as Z, right? So the shopkeeper sold one small size t-shirt, right? Can you read it? Like the shopkeeper sold
one is small, one medium,
one small,
one medium, and two large size shirts.
Two large size t-shirts.
Yeah.
So the total cost is 7, right?
7, yeah.
7. So now you try to form this into a equation. So cost of a small size t-shirt is X. So that means cost of one small size t-shirt is basically what? 1 times X. This is 1 times Y. This is 2 times 2 times Z, which is 7. Similarly, you have 2 more information. So using these 2 information, you will get 2 more linear equations, right?
Correct.
Yes. Is it clear now, or like still you have confusion? Okay, fine. Okay, any other questions?
Yes, sir, 1.3, question number 4. I don't understand the meaning of the hint and the diagram.
1.3, question number 4.
The meaning of the hint.
So the graphs of 2 planes are given, right? some plane, the graph of plane 1 and graph of plane 2 are given, right? In the equation, in the figure.
Yes.
So if they will intersect, okay, if two planes, they will intersect, then they will have a common point, right?
Yes.
So if two lines will intersect, then they will have a common point, right? If two lines will intersect, that means there will be a common point, right?
Yes, but again, what is given?
So here you can see these two planes, they don't have any common point, right?
Yes.
That means they don't have any solution, right? There is no common point, means this equation, these two planes, they don't have any solution. So,
Yes.
so option B is correct, right? So that is what in the hint it's saying, that if a system of linear equation has a solution, then that point corresponds to the solution. Then the point corresponding to the solution must lie on the plane corresponding to each linear equation of the system. That basically what basically is saying, suppose you have a line, this is my line L1, right? This is my line L2. If this line, suppose this is a line y equal to, let's say L1 is y equal to ax plus b, and L2 is a line cx plus d, right? This is line L1, this is line L2. If they will intersect at a point, if these two lines will intersect at a point alpha comma beta, right? Then this alpha comma beta will lie in L1 as well as in L2, right? Correct or not? This alpha comma beta will lie in L1 and as well as in L2, right? So that is what it's saying. If you have bunch of equation, okay, if you have bunch of equation and this system of equation has a solution, then that solution will lie on all the systems. That is what it's saying. That means if you have maybe say if you have bunch of equation, suppose this is your let's say a11 x1, a12 x2, a13 x3 equal to 0, then similarly a21 x1, a22 x2, a23 x3, let's say 31 x1, a32 x2, and 33. So this is a system of linear equation, right? You have three equations. If alpha, beta, gamma is a solution of a system, right? If you put alpha, beta, gamma in the first equation, it will give you 0, right? If you substitute alpha, beta, gamma in the second equation, okay, please, in the second equation, it will also give you 0, right? And also if you substitute alpha, beta, gamma in the third equation, then also it will give you 0. That is what it's saying, that if you have a solution, it will satisfy all the equations. Okay. So in here, in the given question, this this equation basically represent a plane. This equation represent a plane. This equation also represent a plane. That means if alpha, beta, gamma is a solution to this system, that means alpha, beta, gamma is in this plane. Alpha, beta, gamma is also in this plane, and alpha, beta, gamma is also in this plane. That means alpha, beta, gamma is basically intersection of all these three planes. That is what it's saying.
Okay.
Okay, fine. Okay, so I guess any other questions, or shall I?
I have a very small
One
doubt, sir.
Only one option, sir.
Please.
Practice assignment question number 4. I want to clarify only one option, sir.
Practice assignment question number 4. Yes.
How come the third will not be unique, sir? If Magesh tries to find the price of 1 kg potato and 1 kg dal using appropriate matrix representation, that option, no, sir, it is true. Actually, it is a correct answer. How come it will be true, sir? Because it will intersect only at one point.
It must find the price of 1 kg potato and equal to 2 and b equal to 4. So what are the equation you are getting? Can you tell me?
Yes, sir.
What are the equation you are getting?
2x plus 4, 2x1 plus 4x2.
4x, okay, 4x1 plus 4.
Sir, no, sir, 2x1 plus 4x2 is equal to, okay, y is equal to 200, sir. The next equation is 4x plus 2y is equal to 400.
400.
Yes, sir. Here the slopes are different only, no, sir. Then it will be unique.
Yeah. So this is basically what? This is your this is basically your y equal to half
Yes, sir. I
x.
calculated minus half. Okay. Okay, sir. Okay.
This is y equal to
2x minus 100. Yes, sir.
So certainly, yeah, both the slopes are different. So you will get a unique solution.
Yes, sir. But the answer is it will not be unique. That's what.
Okay, let me check option 3, right?
Yes, sir.
So Moez bought 2 kg potato and 6 kg dal.
Option 3 says D is not equal to 400.
No, what I'm asking, yeah, D is equal to 400. 1, 2, 3. No, D is equal to 400. Basically, these two solutions will have only unique solution, right? But in the accepted answers, it shows that it will not be unique.
Yeah. Let me check. So
yes, sir.
So Moez
but I have one thing to say over here.
Yes,
so
please.
Aren't we talking about the same slope?
Sorry?
Aren't we talking about the same slope if we are looking?
If they have same slope, then basically
it will be.
You will have an infinite solution.
So you don't have any solution. Like same slope means they're parallel. Okay. Until unless both the equation are same. Okay. If both the equation are same, then basically you will get infinitely many solutions. Okay. But if both the equations are different and they have same slope, that means they're parallel. So in that case, you will not get any solution.
So it won't have a unique solution. Like it won't have a unique solution because the slope is the same. Just the difference is the.
Yeah, that is what I'm trying to figure out. I'm trying to okay. I just want to check whether whatever the system C form, whether this is correct or not. Okay, so that is what my concern is. 2 kg Moez bought 2 kg potato and 3 kg dal from a shop and paid 200 to the shopkeeper. Gaurav paid 4 kg potato and 4 kg dal and paid D. Okay, so let me form this equation. So the equation is basically
2x plus 2y, sir, actually. 2x plus 2y is equal to
2 kg potato and C kg dal. So that means C y, and he paid 200, right? And Gaurav bought 4 kg dal and 4 kg potato, 4x plus 4y. 4y, and he paid D. So I guess this is the equation. So your equation is incorrect, I guess.
Yes, sir. Your
Yes, sir.
equation is
Yes,
right.
sir. Sorry, sir. I got it, sir. Actually, I calculated with the wrong equation, with the
Yeah,
first
yeah.
choice.
So now,
Okay,
now
sir. I
you
got it
can,
now. Now the
yeah.
slopes are same.
Yeah, yeah.
Okay,
Now
sir.
Okay,
Sir,
fine.
I had doubt in sixth question in the
Thank you, sir.
same assignment.
Yes.
So
Sir,
sixth
just
question
one
in the
dot,
same
sir, in the same
assignment.
question.
Okay, sixth question I have already said twice. Okay. So
Okay, then I'll see the recording.
Sir, just one question, sir, same question. Just one dot, sir. Sir, I formed this equation, sir. The second equation we have written 2x plus 2y is equal to 200 and 4x plus 4y is equal to 400. So after we got this equation, sir, then how last option will get correct, sir?
So this is the equation you got, right?
Yes, sir. Yeah.
Okay, let me then read the last option. If Moss tries to find the price of 1 kg potato in 1 kg jal using the appropriate matrix representation by taking C equal to 2. Okay, C equal to 2 and D is not equal to 400. So C equal to 2, right?
Yes.
That means x plus y equal to minus x plus 200, right?
Yes.
And here y equal to
Minus 4x plus d.
4x plus 4.
Minus 1.
D equal to minus x plus d by 4, right? Let me read whether I made mistake. So yeah, so this so it's given that D is not equal to 400, right? That means d by 4 is not equal to 100, right? Correct or not?
Yes, sir.
That means these two lines, they are different line, right? These two lines, they are different line or not? See, d by 4 is not equal to 100, and here you have 100. Right. So these
they are different.
They are different line and they are parallel, right? That means these two lines, they will have no solution, right? You have two distinct parallel lines. That means they will never intersect, right? That means this system has no solution. Clear? Okay, fine. Okay, any other doubt? Okay, then I'll stop the session now. Okay.
Thank you, sir. Thank you, sir.
Thank you, sir. Good night.
Good night.
Yeah.